I wanted to go over the Pinacol rearrangement, which is an interesting reaction that involves a rearrangement, as the name suggests. This is usually studied in the context of alcohol reactions because it involves a vicinal diol, also known as a glycol. Basically, a vicinal diol is where we have alcohols on neighboring carbons. You can think of the word vicinal as meaning vicinity. They are neighbors. The Pinacol rearrangement, like I said, it's a rearrangement. You can think of it as a synthetic transformation, however, which is potentially extremely useful in various syntheses. So what I want to do is I want to go over the mechanism and explain the logic behind it. And we'll look at it from the big picture as what it means as far as a synthetic transformation is concerned. And then we'll look at a slightly more complicated example, a slightly more complicated implementation of the Pinacol rearrangement. And we'll see if we can apply the understanding that we got from studying the mechanism to figuring out how this slightly more complicated transformation might work. So to start, what's shown on my screen right now is the canonical Pinacol rearrangement, starting with a vicinal diol called Pinacol. It's a tetramethyl glycol, basically, a tetramethyl dialcohol. And what you can see is that under acidic conditions at 100 degrees is we get a rearrangement. And what I always like to do whenever I present a new reaction like this is look at the big picture and see if we can figure out what is the overall transformation. What is changing? And what we can see is that, if I zoom in here, two major things are happening. First of all, is one of the alcohols is being transformed into a carbonyl. I guess it's really three things. One of the alcohols is being transformed into a carbonyl. One of the alcohols is gone in the product. We're losing an alcohol somewhere. And one of the methyl groups is migrating from one carbon to the other. Now, in the case of Pinacol, which is which really doesn't matter. Which alcohol gets converted to a carbonyl doesn't matter. Which alcohol comes out doesn't matter. Which methyl group migrates doesn't matter because it's a symmetrical molecule. Whichever side something happens to doesn't change the overall product. We could have essentially mirrored this transformation and the product would be the same. However, what we'll look at after this in our slightly more complicated example is how you have to approach the Pinacol rearrangement when you have some other non-symmetrical or more complicated molecule. But first, now that we've seen what the overall transformation looks like, let's walk through the mechanism and try to understand how and why this happens. And what I hope to show you is that it's a very instructive reaction where you can learn a lot about mechanisms in general. In fact, if you've studied just a handful of mechanisms at this point, you will probably understand all of the steps in the Pinacol rearrangement, and you actually will be able to figure out the transformation on your own. You can kind of follow your nose. Every step in the transformation is, again, logical and follows by necessity from the previous step to the next step. So let's take a look at this. Lesson number one from this is look at the reagents. We've got acid and heat. And the first lesson is that under acidic conditions, the most rapid type of reaction or step in a mechanism would be a proton transfer. Proton transfers happen much more rapidly than any other type of mechanistic step. like a substitution or a leaving group leaving, or a hydride shift or a methyl shift. So anytime you have acidic conditions, for the most part, a proton transfer will be your first step. It's the most rapid step, and it's pretty much going to get the whole reaction started. So let's do that. And now if we look at the starting material, we really only have one option for where the proton transfer happens. And that is with the alcohols. These alcohols have lone pairs. Being highly electron rich, they will be attracted to a proton from our sulfuric acid. So let's pick one alcohol. Never do two protonations at once. Even if you do have two protonations, they will happen in sequence. So never do all of them at once. So let's just pick an alcohol and we'll have it undergo a proton transfer. So I'm going to start with the alcohol on the right. We'll show this alcohol grabbing a proton. Okay. Now, what will that get us? It's just going to be the protonated version of this. So what I'm going to do is I'll just duplicate our structure. And as a result of protonating the alcohol, we now have water, and our oxygen has a positive charge. So from one lesson, the understanding that proton transfers are very rapid and are typically the first step in an acid catalyzed reaction, we've produced water as a leaving group. So from here, where do we go? Now, even if you don't know what the product looks like, even if you don't know our ultimate destination, you can still guess what the next logical step is. Water is a good leaving group. We've just made water. We've got 100 degrees Celsius, boiling point of water. It should be easy to drive this off at this point. So let's show water leaving. So at this point, water is going to leave. And our new structure now, we have a carbocation. Now, this is important because you have to think about this from the perspective of the product. Why does water want to leave? Well, it's a good leaving group, fine. We've got lots of heat to drive it off, fine. But ultimately, this gets us a tertiary carbocation, right? Our carbon bearing the carbocation has 3 carbons on it, okay? It's very stable because of that. And whenever you have carbocation formation, you need to take that into account. If your carbocation is not stable, it's not likely to form. If your carbocation is stable, it's extremely likely to form. And in the case of Pinacol, we get a nice stable tertiary carbocation. Now, from here, a couple things could happen. Either water could come back in and attack our carbocation, kind of like the second step of an SN1 reaction. The water that just left might perhaps come back in, attack the carbocation, and we're going backwards now. So even though it might happen, it's not interesting to us because it doesn't make any significant changes. It doesn't push the reaction forward. All of these steps, you could consider them as being not necessarily a one-way street, but rather an equilibrium. So water might come off, come back on, come off, come back on. it's an equilibrium. It doesn't necessarily drive us forward. But there's another thing that can happen. If you're thinking perhaps the conjugate base does something, for example, since we've protonated our water or protonated our alcohol to make water by using H2SO4, we've got a conjugate base, HSO4 minus, which is a poor nucleophile. It's big, it's bulky, it's extremely weak or stable, however you want to think of it. So typically speaking, HSO4 minus is not reactive. So even though it's around, we're not going to worry about it. But something else can happen, as per the namesake here, is this is a rearrangement. And you'll notice that if you look at our product in the overall reaction, remember we noted that a methyl group migrated. But again, even if you don't know that, even if you did not see the product to begin with, it's a very logical idea. Why would a methyl want to migrate at this point? Remember that anytime you have a methyl shift or a hydride shift for that matter, or a ring shift for that matter, the only reason it happens is when the carbocation would be more stable as a result of it. Now, tertiary carbocations are excellent. They're very nice and stable. They're easy to form. But there is another type of cation that is even more stable than a tertiary. And that's a resonance stabilized carbocation, a cation whose charge is delocalized or spread out by resonance. And we can get one at this point. So the reason that we have a methyl shift is to make the carbocation more stable. So what I'm going to do, we'll take this methyl in the top left. It could be the methyl, remember, on the far left. It doesn't matter which it is. They're identical. So let's just take this methyl group. Oops. So let's just take this methyl group and move it. I mean, there's a different color here just to make it a little more clear. So this methyl group is going to move there. And over here, let's color these. Protonate. Water leaves. We have the tertiary carbocation. The methyl group migrates. Let's look at what we have now. So after our methyl group moves, it's no longer on that carbon. It has now migrated to the right. So that carbon that gained the methyl group is now happy again. It's got 4 bonds. It's got an octet. No more formal charge. The carbon that lost the methyl group now has the formal charge. It's got a positive charge because it's lost a bond. Now, why is this more stable? It's not strictly tertiary. It does not have 3 carbons attached to it. However, it does have an oxygen with a lone pair that can be donated. So here we have a resonance structure. We can take the lone pair from the oxygen and show that lone pair being drawn towards the positive charge to create a double bond. And in doing so, delocalize the charge. So now we have this. I'll redraw it. Then we get the C with the double bond O. Don't forget that that oxygen still has the H on it. It's got 1 lone pair now, and therefore the positive charge is on the O. and then the C with our 3 methyl groups. So the lesson here, which you've probably learned at this point in some other context, is that a resonance stabilized or resonance delocalized cation is more stable than a tertiary. If it wasn't more stable, if that tertiary carbocation was instead more stable than the resonance stabilized one, then there would be no motivation for the methyl group to move. Remember, there's an energetic penalty for migrations. It costs energy to do that. Now, a hydride shift is minimal energy, but it's still an energetic penalty. A methyl shift requires even more energy to do so. So in order to do that in the first place, there has to be a payoff. And the payoff is an increase in stability. So the methyl group moves so that we get a resonance stabilized carbocation. And now what you'll notice, again, if you compare this current structure to our overall product, you see that now we've got the 3 methyl groups where we want them, and we've got the C double bond O at this point. It's in a resonance structure, but it indicates that there is significant double bond character there. Furthermore, if we look at which of these 2 resonance structures is better, the structure on the left is better. Why? Because all of the atoms in the resonance structure on the left have octets. Okay? Even though the positive charge is on the O, technically not as good as the positive charge being on the carbon based on electronegativity, but the octet rule typically wins over electronegativity concerns. So it's better to have a positive charge on the O if the carbon can then have an octet. Then it's better then to have the carbocation missing an octet. Okay? So that's actually going to be the dominant form. So this is going to be the major contributor. We'll write that in major contributor. That's our major contributor. All we have to do at this point to get to our ultimate Pinacol product is remove the excess proton from the oxygen. And this can happen either by the conjugate base of sulfuric acid, so H2SO4 could do this. Also, water could do this, because remember, we did push off a water molecule. So we have 2 weak bases floating around. Which one you choose, I don't think typically matters. Your professor may or may not have a preference for this. I'm just going to show water doing this. We'll take water. It's going to use one of its lone pairs to remove that H, return the electrons to O, so it removes it as an H+, returns the electrons to the O. And ultimately, our product is what's called Pinacol-one. So the ketone product of the Pinacol rearrangement Pinacol-one. Okay, so that's the product, and that's the mechanism of the Pinacol rearrangement. Again, very logical, right? Proton transfer, very rapid. We protonate the most basic or electron-rich portion of the molecule, one of the alcohols. After protonation, we have water. Water is happy to leave because it generates a tertiary carbocation. The tertiary carbocation is furthermore made more stable by undergoing a rearrangement where the methyl group migrates from the neighboring carbon to the carbocation. That gets us a resonance stabilized carbocation on the carbon bearing the remaining alcohol. Okay, the resonance structure is achieved by donating a lone pair from the alcohol to the carbon to make a double bond. That gives us an all octet structure. And from there, the excess proton is removed by water or HSO4 minus to give us pinacolone. Okay, so that's the logic behind the mechanism. And we can think about this as being a synthetic transformation. It's not strictly a mechanism just for curiosity's sake. We can say, oh, isn't that fun? Look what Pinacol does. It's much more than that. The pattern here is that if we have a glycol, okay, a vicinal diol, like we do in Pinacol, we can transform that into a carbonyl, probably a ketone, but a carbonyl adjacent to a quaternary carbon, basically. A carbon with 4 carbons attached to it. Thinking about this from a retrosynthetic perspective, where if your goal is to have a carbonyl, like a ketone, adjacent to a quaternary carbon, you can do that. You can achieve that pattern by starting with the corresponding glycol and then undergoing the Pinacol rearrangement using conditions as acid and 100 degrees Celsius. Okay. So think about it from the big picture. You say, if I want my product to look like this, I can get there by having my starting material look like that. And then H2SO4 and heat, you get the transformation. Okay. So it's a useful synthetic transformation from that perspective. Now, like I said before, your particular case will not always be as simple as Pinacol because it's symmetrical. We don't have to worry about which side reacts first, which alcohol gets protonated, which group migrates. It's all the same either way in Pinacol. So let's look at a slightly more complicated example, which I've got down here. So I've done one thing here. I've basically taken Pinacol and I've replaced a methyl group with a phenyl group. And this is going to change the dynamic of things. It's going to change the logic and some of the decision making that we're going to have to do. So the question is then, if we react this starting material with H2SO4 and heat, what will the product be, right? Okay, now there's a couple decisions we have to make. The first decision we have to make is which alcohol is going to get protonated. Thinking back to the Pinacol mechanism, how did it work? What was kind of the big picture? The alcohol that gets protonated, right here, is the alcohol that becomes water, which then leaves, which is on the carbon that gets the carbocation. So that's kind of our logic. We're going to say, where do we want the carbocation to form? Or where would we expect the carbocation to want to form, right? So let's go look at our example here, or our test case. And let's consider both possibilities. Let's say that the alcohol on the carbon with the phenyl group gets protonated. Okay. What's that going to give us? Well, it's going to become water. The O now has 3 bonds and 1 lone pair. Remember, it had 2 lone pairs to begin with. So that's water. It's going to have a positive charge. And water is going to leave. Okay. That's one option. So here water's gone. We've generated our carbocation on the left carbon. Now this is an excellent carbocation. It's benzylic. And remember that the order of stability of carbocations typically has the benzylic as the most stable. Why? Because it is delocalized throughout the benzene ring. That carbocation, through moving these pi electrons, can delocalize the positive charge through the ring. It's also tertiary, right? The carbon bearing the carbocation has 3 carbons attached to it. So it's tertiary and benzylic, extremely stable. So the question is, if this happens, what's the rearrangement? Right? What's the motivation for a rearrangement? There's got to be motivation for the rearrangement. Otherwise, no rearrangement will happen. The carbocation has to get more stable as a result of the rearrangement. So if we consider that, right, what would the rearrangement have to look like? Well, one of these methyl groups would have to move. So let's say that this methyl group moves. We lose our benzylic cation, right? Our carbon now would still be resonance stabilized. It would be resonance stabilized by the alcohol, but it would not be benzylic anymore. So there's really no motivation for the methyl group to move at this point. And so it doesn't. Now, if it can't rearrange, then obviously we aren't getting a Pinacol rearrangement. But notably, there's also nothing else that can really happen. What else do we have? We've got water floating around. We've got HSO4 minus floating around. And at this point, essentially nothing can proceed. What might happen, as I mentioned before, because this carbocation won't rearrange, it's just going to sit there. And eventually, water's likely to just add back in. And now we've got equilibrium again, right? Now we've got a forward and a backwards reaction. But we never get anywhere. We're never going to proceed to a new structure. So the point is here that might be the most likely pathway. The most likely pathway certainly might involve protonation of the benzylic alcohol, leading to water leaving, leading to a benzylic cation, but that's it. At that point, water just adds back in. We get back to the protonated form that might deprotonate and get us back to the starting material. So that's a great pathway, and maybe that happens 99% of the time. But it doesn't get us anywhere, so it doesn't matter. Okay? Let's consider the other option. Let's consider what might happen if the other alcohol gets protonated. So let me just copy this. Okay. And I'll just make a note here. We'll say reaction won't proceed. essentially the carbocation's too stable. It's got nowhere to go. And so nothing's going to happen. All right, but what if we protonate the other alcohol? So this O gets protonated by the H plus. That generates our water with a positive charge. And that's going to leave. Now we've got a less stable carbocation than we had before, which means that this pathway is probably less likely to happen. But when it does happen, maybe the one time out of 100 that it does happen, we can proceed to a new structure. Okay, so now we can undergo the methyl shift. We'll have that methyl group migrate. What does that get us? Our methyl group here is gone. It's now migrated to the neighbor. And now we not only have a benzylic cation that is stabilized by the adjacent ring, it's also stabilized by resonance from the oxygen. So we've got a new structure, a novel structure that we wouldn't have ever gotten in the previous pathway. So here we have resonance, making sure we use the resonance arrow, and don't confuse resonance with equilibrium. Don't confuse the resonance arrow with an equilibrium arrow. They mean very different things. So here's our product with our methyl. We've generated the double bond to our oxygen, which has the positive charge now. And again, this is the major contributor, because all of our atoms have octets. Okay. And so finally, actually, I'm just going to draw this hydrogen explicitly. In our last step, we can have something like water. Remove that excess proton, returning the electrons back to the oxygen. And our product is the rearranged product. So notice our pattern. We've got our carbonyl, again, it's a ketone, adjacent to a quaternary carbon, which is, again, the general synthetic transformation of the Pinacol rearrangement. So it's a little bit deceiving in this case. Since we've got an asymmetrical structure, we have to consider both possibilities. One possibility leaves us with a dead end, right? The first possibility that we considered left us with a carbocation that had nowhere to go. It was already in the more stable position and so never yielded a unique structure. We just ended up at equilibrium with the water. By proceeding through what is initially the less stable intermediate, initially proceeding through the less stable carbocation, the tertiary one, not the benzylic one, we can undergo a methyl shift to get an extremely stable, more stable than your standard benzylic cation would be. And from there, we yield a unique product. If I were to draw the reaction energy diagram for something like this, it might look like this. What I'll do is we'll draw an energy diagram, but we'll kind of start in the middle of the diagram. And we'll move left or right. So here's our energy diagram. We're going to have energy on the y-axis. We're going to have our starting material somewhere in the middle. Now, in one pathway, we'll call it the blue pathway. Move this over a little bit. In the blue pathway, we might go one step and get to a low energy state. This was the benzylic cation. In the other pathway, the second one we did, we'll call it the green pathway. We didn't go as far down in energy in the first step. Okay. We first went to a tertiary. And then in the second step, we got to an extremely stable state, which was the benzylic plus the oxygen, right? Our second product. Now, whether or not this transition state is higher in energy or not doesn't really matter. Let's imagine that it is. Let's just say that this goes way up in energy and then doesn't get us to as low a state. You can see the idea, right? Most of the time, and this second step is the shift. I'll just write that in there. That's the shift. Most of the time, this reaction is most likely to proceed through the blue pathway, but it doesn't get us anywhere. The only option the blue pathway gives us is to return back to our starting material. Whereas if we happen to proceed through the green pathway, we will end up in a new position, which is low enough where we wouldn't be reversible, right? We go through a lower energy pathway, but in order to get there, we have to get over a higher energy of activation. So the kinetics, the thermodynamics, that's more of a general chemistry concept, but it applies to these types of ideas that even if the most, maybe the most likely pathway doesn't necessarily get you anywhere, every once in a while when you cross over into the less likely pathway, you get a new product. Okay. Hopefully that was useful. Remember the ideas here. Let's go back and review the major concepts. First of all, Pinacol rearrangement is the conversion of a diol, a glycol, into a ketone or carbonyl and a quaternary carbon center. Okay. It proceeds by doing a protonation as the first step, followed by loss of water, a methyl shift or a rearrangement, a hydride shift perhaps, to increase the stability of the carbocation by giving us a resonance stabilized structure. From that, deprotonation of the proton from the oxygen to yield the carbonyl. Again, getting us a carbonyl adjacent to a quaternary center. When you apply that to any arbitrary structure, any perhaps non-symmetrical glycol, you need to consider, first of all, where the most stable carbocation can be formed, and if that carbocation gets you to a novel structure. In this case, the most stable carbocation that can most immediately be formed is a benzylic cation whose rearrangement whose stability cannot be improved by rearrangement, and so we get nowhere. We end up just at equilibrium with water. However, if we go through what is initially the less stable carbocation, we can then get a methyl shift that leads to a more stable carbocation, one that is more stable than the original one was in the first place. Plus, we get a novel structure, which can then proceed to make the carbonyl at the end. In doing this, you need to consider all those factors. You need to consider what your final products might look like, but also remember to use this as a potential synthetic transformation for generating a carbonyl adjacent to a quaternary carbon.